without delaying anymore, I'm going to introduce Dr. Nash, and she is going to come and introduce our speaker. Dr. Nash, the floor is all yours. Let everybody.
I will do that. Thank you. Good afternoon, everyone. I am Dr. Kylie Nash. I am the Director for Web and IT Communications in the IT department, but I also serve as the NSBE advisor for the AAMU chapter here. NSBE is the National Society of Black Engineers. And so, and of course, other duties as assigned. So I have known Mr. Garrison Best for about 3 years, and I've known him through NSBE. And he started out as a senator, a member, and then now he's the president of the NSBE chapter at A&M. So I've watched him grow and mature as a young man and a leader as well. So I would like for you all to join me in welcoming him as he does his presentation from his internship from SAIC this summer on cybersecurity. So let's give him our attention and a welcoming round.
Hello, everyone. My name is Garrison Best. I'm a senior computer science major with a concentration in cybersecurity here at A&M. Thank you for everybody for coming out today for this presentation. So today I'm going to talk about my cybersecurity presentation that I did at SAIC this summer. I had an opportunity to work with some students from different universities. So I'm going to kind of get some based on what schools they came from and kind of what they did. So first, our mentor, Ike Clinton, he graduated from the Citadel. He's a full-time student at SAIC, and he was like our mentor over a student body. He was a recent grad. And then me, I told you already, I'm a computer science major with a concentration in cybersecurity, and this was my internship that started in May. And I was working with the IT infrastructure. Justin Richardson came from James Madison University. He's an intelligence analyst major. He started an internship with me in May, and he did the industrial control systems. I'm gonna get more into what my presentation's about after. And then last, Jake Engel from Troy University here in Alabama, and he works in global business, and his minor is in cybersecurity, and he did the briefing and the risk vulnerabilities for this presentation. So basically, our presentation is about, what I'm trying to talk to everybody about is our vulnerabilities of how the Internet of Things is controlling the world, and how cybersecurity is plays a big role in how technology is growing. So I'm going to define Internet of Things, and I'm going to show you some simple vulnerabilities and different levels of IoT, and then I'm going to show you our scenarios and what we actually did in our presentation. So what is IoT? So IoT is in cars, industrial systems, smart homes, computers, in Wi-Fi in your like our buildings, like this building, how we connected by Wi-Fi, your phones, smart TVs, smart meters, smartphones, and even your control systems and healthcare. So these are all Internet of Things. Everything that's connected by technology is considered Internet of Things. So this is basically like just a definition if you guys want to read that. So first I have a little video basically to kind of introduce you to what I'm trying to talk about today. Okay, so the cool thing about this, you kind of saw the things that cybersecurity and what you can do as a hacker and what they've done over time. One of the cool parts about that video is the video about the vehicle hack with the Jeep. I was actually working with Chrysler when that happened, and so I actually had to do the security stuff to fix the problem. So just to see how real it really is, you actually have to go through stuff like that. So that was a cool opportunity. So first, this part is about vehicle vulnerabilities. So you kind of saw the kind of things that happen with different businesses, but also vehicles. People can do different things. You can take control of a car, you can shut a car off. That's basically what vehicle vulnerabilities are about. Your IT infrastructure, this is what I'm gonna be covering later on in the presentation, but basically anything dealing with computers, phones, anything dealing with your technology you use every day, it has a vulnerability to it and can be hacked. And then critical infrastructure. The biggest thing that I want to talk about is Stuxnet. That's what our presentation is based off of. So Stuxnet was this big worm. Basically, somebody, they don't know who, somebody put a USB down on the ground in Ukraine, and somebody picked it up and plugged it into their computer at work, and it actually sent a worm through their whole server and crashed their whole system. So it's just some simple thing that some code could do for all the computer science majors. You can like control certain things. I wouldn't advise you do that, but that's the kind of things that kind of happen. And at the bottom, it shows you that if you're familiar with the military, that cyber is actually putting its way into the group of how the military works. So my scenario, real quick, is going to be based off of Stuxnet. And we did, basically, a hacker is going to compromise a vehicle. The vehicle is going to push malware into a smartphone. And then the phone is going to be taken into a business, infect the IT network, and it's going to go onto the OT network and actually take over the critical infrastructure. So for our vehicle presentation, what we use to actually get into the vehicle, we use the OBD2 port, which is basically every car has it underneath their driver's side that you plug in, they do your diagnostics, they plug in to figure out if something wrong with your car. So we actually use that to get into the car. So I'm gonna show you some demonstrations of how this kind of works. And this is, I was talking about the CAN bus, if I go back. The CAN bus system is what the OBD2 port connects to, which is basically like a computer in your car that controls all the components and everything. So that's what we're focusing on, working on the CAN bus to actually take control of the car. So these are the different things that use CAN bus in our everyday life, trains, aircrafts, and then industrial automation. So this is actually a demonstration. Ike Clinton, who did this presentation, was in his car, and it says his lights, or his door is open and his lights are off. And he's gonna show you in a minute that they're actually not on. They're telling you to turn them off, but they're actually not on. So he's gonna go outside the car to show you that they're actually not on. That's, of course, you know, your car, that's how they look. So he did this through the OBD2 port, and he basically sent some code into it to make it believe that. And this one is another simple one. It says the door is open, but the door is closed. So it's just basically just freaking out the system, saying that there's something going on. So this is my component, IT infrastructure. These are the different components of IT infrastructure. I'm going to focus on mobile devices. So in our presentation, we basically, you plug a phone up to charge it in your car or connect it to like your Wi-Fi or whatever, and it, from the vehicle, what he used, it put malware onto the phone. And so, and then I'm gonna take the phone into a network to actually take over. This is critical infrastructure. The part we're trying to get to is control infrastructure. So these are different components of that. We're focusing on the oil refinery for our presentation. I'm gonna skip through some of this stuff. Oh, snap. Okay, so let me see. Okay, so right here is a software we call Sophia. Sophia is basically used to show you a network. So you can plug up your Wi-Fi network or your network that you're on, like in AAMU, and actually watch traffic from this application. So this is what we actually use to monitor the hacks that we did in this presentation. The next part of the video will show you, it'll go on, it's just moving kind of slow. So for this presentation, I use Kali Linux, which is an open source tool for penetration testing for cybersecurity. So it's open to anybody, you can get it for free, and it has all the different tools that you need to actually do penetration testing, any hacking abilities. Okay, so right here is when, this is from the phone. So basically this is a computer, but we're using it as a phone. So what I did, I sent an mmap to the network from the phone, from the computer that I hacked into. And you can see this rainbow effect sending onto the OT network here on this side right here. In a minute, you're gonna see stuff get pinged back to the computer that I was using. So what this is basically doing is, when I sent this mmap out, I was trying to find out what was on the network so I can actually hack it. So I found out that there's 3 components there and which one I wanted to actually access. So I was trying to get to a component of control system to actually take over this component to take over the oil refinery. So now, being logged into the computer, we're going to, if they run the command. So I believe the computer I'm hacking into is that one right there. And so you can see right here that it has an open TCP port, which is used for SSH. You can SSH into the component to actually take over the device. So this is the control system that one of my colleagues made. So basically he's running it normally, letting the oil come down. He can open the valve in a moment to actually make it go down into the separator. So now see, it's running, and this is how control systems actually work. They're run based off of Wi-Fi that you can log in at home, and anywhere you have Wi-Fi, you can actually log in and do stuff for big corporations like this. So he's actually controlling it from another computer. So what I'm actually going to do for my hack is actually take over this and make it so he can't control this control system. So right now, I'm actually going to send a command to actually take over the control system. So you see, take over the PLC, and you'll see this command get sent over, and you're going to see this long string of data. That's the computer that I'm on, controlling. That's the network where everything's getting controlled, and that's my computer that I hacked into from over here. So I'm controlling this, and I'm sending commands here. So it's going to go back to the control system after this. Yeah, so now he's pressing stop to try to stop it, but he can't because I took over the control system. So now, if you think about it in real life, if I was to do this at an oil refinery or, like, say, a water factory, and I overflow all the water bottles and everything, they're losing money. So he can't stop it, he can't control it, he can't do nothing for it unless they, like, actually shut the system down in the site. And they would never know I did it because they have no backtrack of my phone that I hacked in through the car. So this is kind of some of the stuff that can happen with hacking. It doesn't take a lot, but I mean, of course, you're supposed to do it professionally and in a way that you're not supposed to get arrested for. So I'm not telling anybody to go out and start hacking stuff to try to change grades and all sort of stuff. Don't do that. But in conclusion,
for the past few months now, the nation's top military, intelligence, and law enforcement officials have been warning Congress and the country about a coming cyber attack against critical infrastructure in the United States that could affect everything from the heat in your home to the money in your bank account. The warnings have been raised before, but never with such urgency, because this new era of warfare has already begun. The first attack, using a computer virus called Stuxnet, was launched several years ago against an Iranian nuclear facility, almost certainly with some U.S. involvement. But the implications and the possible consequences are only now coming to light.
I do believe that the cyber threat will equal or surpass the threat from counterterrorism in the foreseeable future.
There's a strong likelihood that the next Pearl Harbor that we confront could very well be a cyber attack.
We will suffer a catastrophic cyber attack. The clock is ticking.
And there's reason for concern. For more than a decade, the U.S. military establishment has treated cyberspace as a domain of conflict, where it would need the capability to fend off attack or launch its own. That time is here because someone sabotaged a top-secret nuclear installation in Iran with nothing more than a long string of computer code.
We have entered into a new phase of conflict in which we use a cyber weapon to create physical destruction. And in this case, physical destruction in someone else's critical infrastructure.
Any questions? Well, thank you, everybody, for allowing me to talk to you guys.
You know, we build up our society and our infrastructure based upon all these things. We want to make things easier, make them more accessible, do things more quickly. We use computers to connect everything together and share information over large distances through these networks. And on the surface, it sounds pretty good, it works pretty good, but it also leaves yourself vulnerable, and that's what cybersecurity and all that is all about. I'm an old Star Trek person. I know some of you some of you don't even know what that is. But the chief engineer on there is a guy named Scotty, and he said that the more complicated the plumbing, the easier it is to stop up the drain. And that's kind of like what's happening with cybersecurity, but we need students like you learning about it. There's a whole area also called cyber forensics. And as you heard Garrison say, you know, they couldn't catch him because they didn't know how he put it on his phone and all that. But there are people in cyber forensics who figure that stuff out and track and go backwards and go backwards. And we need to be able to do all of that because we've left a lot of important critical things vulnerable if we don't. Don't go far, Garrison. We need to show our appreciation. Let's give Garrison another hand. That was a great presentation. And just recently, we had a couple of teams involved in a hackathon over in Atlanta, the NSBE one, and then Google sponsored one as well. There were multiple teams in both of those competitions, and I believe our teams in both cases actually got second place in both of those teams. Also, Garrison is forming a team to participate in a hackathon at Stanford. Is that correct? In February. So if you are so inclined with this kind of thing, you might want to talk to them. But also, in a broader sense, you students who are involved in projects, Dr. Chan, where are you? This is the director of our Special Projects Laboratory. We've always got something interesting going on there. All the faculty members, raise your hands, faculty members that are here right now. They're all got things going on. So get involved with them and then come up and talk about it. Don't be afraid to tell your fellow classmates and constituents about what you're doing. Okay, so this is a certificate of appreciation awarded to Garrison Best for your contribution to the Dean Speaker Series presentation, Science Applications International Corporation internship for 2016. So. Garrison also takes care of the newsletter that we put out of the college. So if you happen this month, his picture will probably be right at the top, big picture for this. But good job, thank you. Okay, we're going to move on now to our keynote speaker, and it's really great to see all of you here. I'm glad we packed out the place. I am very proud of you all for being here, and I'm asking you to give your attentive ear to our next guest. Now, I'm particularly interested in this topic from Dr. Paul McConaughey, and this is NASA's exploration systems and the journey to Mars. So I'm definitely going to be listening to hear what he has to say about this. But let me just read what's here. Dr. Paul McConaughey is the Associate Director, Technical, supporting the Office of the Center Director at NASA's Marshall Space Flight Center in Huntsville, Alabama. So he's right next door. Named to the position in August 2015, Dr. McConaughey provides expert technical advice and assistance to Marshall Center Director Todd May in support of the entire body of engineering, science, and propulsion work conducted at Marshall. So that's a big, gigantic responsibility. He performs special studies, advises, and assists in policy review, manages and reports on center-wide metrics, and develops new technical benchmarking strategies. He develops new he works closely with senior managers in all these endeavors, ensuring Marshall programs and projects are timely, technically sound, and serve the goals and requirements of the agency of the nation. Now, how much of your homework is timely, technically sound, and serve the goals and requirements of the class? That's expectations that you have at this level. So, but building that kind of mentality and philosophy about how you do things starts now. So if you want to put yourself in a position like this, you start acting like that now. His NASA career began at Marshall in 1986 as a mathematician in the Systems Dynamics Laboratory. Is Dr. Majid here? Did she make it? That's our coordinator for our math program. So we have some math people here. He was in the Systems Dynamics Laboratory for his service to NASA. He has received 3 NASA Exceptional Service Medals, a NASA Outstanding Leadership Medal, a Center Director's Commendation, and a Certificate of Appreciation. McConaughey also received the Presidential Rank Award for Meritorious Executive in 2011, the second highest award conferred by the President of the United States. You ought to get a hand for that. That's all right, don't be shy. We like to give people their flowers while they can smell them. McConaughey earned his bachelor's degree from Oregon State University in Corvallis and a master's degree and doctorate from Cornell University in Ithaca, New York. So with all that said, let's give a warm welcome and a round of applause to Dr. Paul McConaughey.
So thank you, Dr. Glenn. It's very much an honor to be here at A&M today. A&M and I go a little ways back. I remember running 10Ks on your hills, and I can tell you your hills are hard, and it's hard to get up here sometimes. But it's certainly a great community of students and faculty here that really is a center fabric of universities in the southeastern United States, and also congratulations on being selected into one of the top 100 engineering schools. Also, at a day-by-day basis, it's A&M's a part of my life because I think y'all have a great radio station, okay? And I think you take credit for the win this year in the Classic. So that was also a great win for the community there. So today I'd like to talk about NASA's exploration systems and our journey to Mars, okay? And so the question is the journey to Mars just a movie? Is it just a vanity, or what's the issue there? Really, the derivation of NASA Mars policy goes to President Obama, when in 2010 he established a national space policy where he presented a KSC that said basically NASA will be going to orbit and set foot in Mars in the 2030s. The first round would be in orbit of Mars, and then feet on the ground in the mid to late 2030s. He announced this at Kennedy Space Center in 2010, and they then followed up with that, reiterating that at the Space Frontiers Conference in Pittsburgh just this year in 2016, where he then got to see a chance to see some of our hardware that was in development. We put it on display up there, and he reiterated his policy for having the U.S. move with other countries to a Mars mission. Fortunately, the support for this vision was also established through the 2010 NASA Authorization Act, which was a joint effort by Congress and the House and the administration to fund this activity. So the good news is for this Mars mission, we've had pretty good stability over the last 6 years, and that's important because developing these capabilities for the nation takes on the order of 1 or 2 decades. So I'd like to talk a little bit about that today. So the question, why Mars? Okay, is it just something because it's a good sci-fi story, it's a good book, it's a good movie? In reality, it's the only planet that we think humans can live on in this solar system. The keys on Mars is that, number one, we can live there. 2, it also has resources that are key to human life. 1, we know there's CO2 there. We can generate oxygen from that CO2 through reduction process. It has methane, and we also know that there was water on the planet at one time, so consequently there may be water there in the current form and fashion. So there are some resources there. It also has a reasonable gravitational field on the order of 5/8 of the Earth. You know, you can actually land on the ground, and so it does give us some hope that people could actually live there. From the science side, it's very interesting because it's both a picture of Earth's past and Earth's future. So with respect to planetary evolution, where Mars was and what it is now is indicative of what potential would be for Earth in terms of depending on how things go with respect to long-term planetary trajectories. So the question is, how are we going to get there? How are we going to execute the vision that the President gave us for the Mars activity? So to execute that, we're starting with what I call our bread and butter transportation system. And these are the Orion space capsule, which you see in the upper left, the Space Launch System vehicle, which you see in the upper right, and then the ground system that supports this. It's not just another rocket. We've seen a lot of rockets around in the community these days. This is a large rocket. It's on the order of the Saturn V that you can drive by on Governor's Drive. It's actually larger, has better performance, and has significantly more throw capability in its evolutionary configurations. So it gives us the capability to put large mass in orbit, put people a long way out, faster, further than they could before in history. So right now, a lot of the effort with respect to supporting this Mars mission is focused on these 3 major programs. The first is the Orion spacecraft, and as you can see here, it's not an unusual look. It's a spacecraft. The capsule is there in the middle. We've seen capsules around. It happens to be a very good configuration for reentry, either at the Earth's surface or the planetary surfaces. But you see that configuration there. On the upper right, you see the abort system with a little shroud that covers the capsule. That's because when we fire the abort system, those rocket motors that are up on that little upper right-hand corner, you generate about 165 decibel environment, which tends to wreak havoc with the avionics and other things behind it. So consequently, we have the capsule shrouded. Below the capsule, you see on the lower left a service module. These are the propulsion and the power and the environmental life control system guts that support the people in the capsule. Now, Orion is unique. It can support 4 people for 21 days in deep space. That's significantly longer than anything we've seen in Apollo. That's more than what you had in the shuttle capability. And in addition to that, if you get in trouble, it has a 7-day contingency capability. That is, if the vehicle died, we could still survive 7 days with a 4 crew and still bring them home if we had a damaged vehicle. So that is a key capability in terms of supporting future deep space missions. We saw the AFT-1 flight of this in December 14. This was an unmanned test flight that flew out of KSC on the Delta IV Heavy, which you see on the left. You see the orbital trajectory there. It was a pretty simple, highly elliptical orbit there, 36,000 miles, 2,700 mile apogee, 4.5 hour flight, but it's the furthest that we've thrown a capsule since the Apollo era, because everything we've had since Apollo has all effectively been in low Earth orbit. So we flew Orion. It was interesting because we thought, as we went past the Van Allen belt and lost our radiation protection of the Van Allen belt, we thought that maybe we'd lose some flight computers. In fact, we predicted a 20% failure rate on our flight computers and with the have to reboot and reentry. Well, it turns out they did not fail. But what did fail is we came in on landing and parachute. We have these capsules can either land upside down or the way we want them to. And it's about a 50-50 probability. So if it lands upside down, we have an uprighting system where a bunch of airbags blow up and it turns the capsule the other way. Well, half of those failed. And so it happened that this time we landed right side up, but even only 2 of our bags on the capsule uprighting system failed, and we're in the process of assessing why and fixing that for the next flight. One of the major tests was the reentry system, the thermal protection system. You're talking about 4,000 degrees Fahrenheit as you're going through the plasma on this reentry. It turns out that upper right-hand corner, upper left-hand center section, the brown, that TPS survived the reentry very well. Actually, it only had about a 1/4 inch charring with another 1/4 inch affected layer beneath that. We had about another inch left of margin in terms of that TPS. So it was a real good test with respect to thermal protection. The other activity we're working on, and this is a Marshall-led activity, is a space launch system. And this is what you see is effectively a combination of a shuttle-derived launch vehicle and a constellation-derived vehicle. It's the only vehicle capable of carrying humans beyond low Earth orbit. Again, 4 folks, 21 days in the Orion space capsule. It is designed for deep space exploration, whether it's putting cargo out there, like on the order of 40 metric tons, putting people out there, or putting large science missions into very deep space. Right now, well, we'll talk about where it is on there. So where we stand on development here, we have various elements of that, and here you see the solid rocket booster test firing. This is a shuttle-derived booster. It's got another segment, so it has significantly more power on the order of 3.6 million pounds thrust. Looks pretty simple, right? We've seen solid rocket boosters fire on the shuttle for years. In reality, this is significantly different with respect to thrust profile, but also we had to change the liner of this material because we were using asbestos insulation. Okay, we all know that asbestos is pretty ugly, so consequently the EPA told us to take it out. As we developed this new vehicle, when we removed the asbestos, we had a challenge with the liner. As we poured the liner and cured it, it was kind of like a polymer type thing. As we baked it out, little gas pockets formed, and when the gas pockets formed between the liner insulation and the propellant, it gave you it led to the possibility of propellant debonding and falling off as you're firing these motors. That debonding would then lead to explosion of the vehicle. So we worked our way through that. It turned out it was a subtlety of the bake-out process and how we applied the insulation, but we have it fixed now. We've successfully fired 2 qualification motors, and we're in the process of casting the flight article for the next SLS flight. We also have the RS-25 core engines. These are derivatives of the SSME. They have an upgraded controller. We have enough for 4 flights in current inventory, and we're also in the process of starting the production line for the updated SSMEs. Where we're going with this engine is we're reducing the part count and combining those parts and replacing them with additively manufactured parts. And with that, we'll then lower the cost by about 33%. And with respect to additive manufacturing for metallics, this is probably one of the harder applications you can do. One where you're trying to retrofit an existing design with additively manufactured parts and then putting them in a very harsh environment. You're talking turbo blades they're seeing like 7,500 pounds horsepower each. And this is a tough environment with respect to hot gases and cryogenic fluids. The core stage is really the main emphasis right now in our development. This is the center part of the vehicle that's being built in Michoud Assembly Facility in Louisiana. It's being designed here in Huntsville and manufactured down south. Here you see on the left side is the fuel tank. It's about 200 feet long. We have both the flight article and the structural test article developed, and on the right you see the LOX tank. So these two will combine together to make the core stage of the vehicle. It is the structural and propulsive background or backbone of the vehicle. Now, these 2 pictures look kind of cool and they're kind of fun, but they're not easy to come by. As we were developing this and putting the robotic welder together, these stacks, these big rings, which are on the order of 27.5 feet in diameter, we're welding these stacks together robotically through a weld that goes around in a circumference. So it's this welder, a robotic welder, it's about 200 feet tall, 30 feet in diameter. The first time it was put together, a subcontractor got the angle wrong at the bottom. So as these four stanchions were going up, they were one was tilted and it didn't quite align. They had to take the whole thing apart and rebuild it. So it cost us 8 months on schedule. As we're getting into the welding now, we're doing friction stirred welding. We're finding now that as we're getting welding these very thick joints in the rings, like 5/8 inch thick welds, we're getting a different porosity in the metal as we go from one direction versus the other on this welder. So we're in the process of resolving that. We think we have a fix in place, but we're still doing some detailed materials testing and coupon testing relative to the weld schedule. So anyway, we think we've got this in place. We've made good progress. We're ready to start testing the structural test articles, and we have developed some of the flight articles. So this will then be the core stage. We put these together, add the engines, that will be then the core stage, the central part of the SLS vehicle. Once it becomes assembled, we then we'll integrate it down at Kennedy Space Center in Florida. On the left side, you see the mobile launch tower. On the right side, you see the crawler transporter. That was the crawler transporter that we used back in Apollo, back through shuttle. As we got into it, we found out that the bearings were wore out, the transmissions were nasty. It's kind of like that old 4x4 pickup that your dad had in the backyard. It actually needed a rebuild, so we rebuilt this whole thing in the last couple of years. Because SLS is significantly larger than Saturn V or shuttle, we actually had to go in and change the whole exhaust trench of the launch pad and the cooling system. So Exploration Mission 1, this is what we're going to fly in 2018. So that's pretty soon, it's a couple years from now. You see the first launch of SLS, and here is a brief summary of the mission. We do a launch on the left-hand side, do an orbit, and then effectively do a trans-lunar burn with an unmanned Orion. So once we do an unmanned burn, we then do a loop around the moon. Okay, and then we go into what we call a distant retrograde orbit. It's a very, very slow, low-energy orbit around the moon, and actually your farthest distance from the moon will be 30,000 miles away. So this vehicle in this test flight will be further away than any other vehicle that's human-rated that we've had in our history. The mission will last like 25 days, so it'll be a very robust challenge for SLS and the Orion vehicle. So that distant retrograde orbit, so remember this distant retrograde orbit. These low energy orbits are the orbits that will be assembling the Mars transportation vehicle. Okay, we're not going to be assembling them in low Earth orbit. It takes too much energy to maintain the structure there. So we're going to go out into a very, very low G orbit out here near the moon, and then do our integration and assembly there before we shoot the integrated system out to Mars. So this is the first step towards that DRO orbit. Also on this first flight for EM1, kind of a little fun thing, we're flying 13 secondary payloads. These are 6U CubeSats that will be tied to the SLS. They'll deploy after Orion leaves, and they'll deploy as a function of time depending on what the mission is. Some of the missions you see are lunar-type missions for these 6U CubeSats. Others are coming back to Earth. We have some international missions. One of the vehicles goes to the sun. Specifically, the one that's going to an asteroid is being developed here in Huntsville and at Marshall. We're actually one of these 6U CubeSats will deploy. After it gets away from the system, it'll deploy a solar power shield array, and it deploys this large modular system. It will then take the solar winds, use that to go for 2.5 years, go to an asteroid, and then photograph the asteroid and send those back to Earth. So those will be some significant payloads generated through the EM1 system. The second mission, EM2, this will be the first human mission of the new system. Will be a 2-lap around Earth. It's very interesting here. You see the green is there. First lap, first orbit, and then second orbit is a larger heliocentric orbit. That will give us time to sort out and test the environmental life control system, because this will be the first launch of the flight system of the environmental control system that has oxygen, water, cooling, heating, what it takes to keep the crew alive. The crew doesn't want to punch the go button for the moon trajectory until they're confident that we have a good ecosystem that works and will keep them alive. So if it doesn't work, we have a few hours to bring the crew back from orbit. So how this all fits together is what they call a journey to Mars is summarized from the Earth to the cislunar environment to Mars on the right. Historically, in my career, we've been in low Earth orbit. That's on the right-hand side. That space station, that shuttle, that's a lot of the comm satellites that we're dealing with here. What we're going to with SLS, and as a proving ground for the Mars mission, is we're going to start doing missions that are significantly beyond the moon in what we call the cislunar environment. And again, this is an environment that's a very low-G environment that we can do integration and assembly of large space structures. It doesn't take much energy to maintain those trajectories, and we can still do significant operations, and they become good trajectories to start the Mars mission. The key on this is how long does it take to get home if you have a problem. Right now, if we have a problem on station or low Earth orbit, you're a few hours away. So that means if a guy gets appendicitis or have a problem or his wife wants to see him for dinner that night, we usually get him home. Once we go to cislunar, we're talking about days to weeks away from home. So if there's a problem out there in space, you can't just come home immediately. So we have to have developed significant capability in situ on that vehicle to support repair or issues as they arise. The goal is to survive a mission for 1 year in cislunar just by itself without having any external resupply or any help from home. Because the Mars mission is a 3-year mission, right? It's take 3 years, you're gone, you get no help. So you have to pre-stage all your logistics, you have to have all your contingencies in place, and if you have something that breaks down, you have to have some capability to repair and come home. To prepare for a 3-year mission, we're looking at a 1-year test in cislunar space. So that's what's called the proving ground, and that's where we're going first with the SLS and Orion, which goes back to that DRO orbit. Remember those long, lazy orbits around the moon? That's what we're starting in that first mission to Mars in preparation for those long cislunar missions. So SLS is an evolvable design to give you a concept of size. You see a person here, and here's the size of payloads. You see the Orion mission, the ARM, and on the far right-hand side, you see a concept of the Mars Trans-Ham vehicle. There in that, that's the size of the cargo that you can put in this vehicle. It's 10 meters in diameter by 35 meters long. It's big, it's heavy, it's massive, and that's what we need to get to Mars. The other thing that this vehicle enables is because it has a very large throw capability, you can throw big, heavy stuff into LEO or into low Earth orbit, or you can take small science missions, like you see on the left-hand side. The small science missions, you can throw those very far. So that's how we're enabling the Europa mission upcoming, which normally would have been like a 7 to a 9-year mission for a science mission. When you fire it on SLS, it only takes 2.5 years. It also enables some interstellar options, i.e. can we get vehicles outside of our solar system in a timely manner? SLS will enable that also. Again, that's just throwing science missions, small science missions, a very long way very quickly. So how do we get to Mars? Okay, this is where I think the challenges come back to you as the folks that will have to execute the Mars missions. How do we get to Mars? Well, first of all, you have to throw about 500 metric tons to low Earth orbit and assemble your system. You have to have a transportation habitation to put the crew in. You have to have propulsion and a power module. You have to have a lander. And once you get a lander, you then have to have a habitation module on Mars. Then you have to have an ascent module for Mars. Put your whole logistics train starting cislunar orbit out to Mars and back. It takes about 500 metric tons. Then you'll be seeing like 6 to 8 SLS flights with supporting commercial flights to put that system together. Once you develop that, you got to figure out what your propulsion system is. Depending on the propulsion system you get, your travel time, your trip time, is anywhere from half a year to a year. So if you go in with nuclear thermal, it doesn't sound like a good ride, but it's actually a pretty good system. You can get there fairly quickly. If you go with solar electric, supplemented by chemical, it could take as long as a year to do that system. So getting there as a propulsion is hard, and then once you understand what your propulsion is, one of our big challenges is just how do you store a cryogenic liquid for 3 years in space? Because the cryogenic fluids are typically what we use for our propellant systems, whether it's nuclear, whether it's chemical, and even the xenon you have to store for a long time. How do you keep those fluids in your system and reliably for 3 years? That's also a large challenge. Then, if you're a human, we have 2 big problems that we must address. One is radiation protection, Once you get outside the Van Allen belts, cosmic rays, gamma rays, X-rays, they can be pretty dangerous, okay? And it's not just a suntan in space, right? These astronauts sometimes historically come back with some significantly higher risk and or evidence of cancers. And so there is concern about putting somebody 3 years out in space in a high radiation environment. What will it do to their health? So we're looking at how do we protect the crew from radiation and or have a safe place in case there's a major solar event that they need to be protected from. That's challenge number one from the human side. Just as big a challenge is reliable life support systems. We've talked about 3 years from being 3 hours from low Earth orbit. Well, in reality with space station, our life support systems are pretty unreliable for some parts. Their life ended up being about 10% of their design life in some cases, and it turns out we had to put a lot of spares, a lot of logistics, a lot of support for station. It takes a lot of overhead to keep the life support systems on station to keep our crew alive. Now, if we go into Mars, we're going to have 3-year reliability and or the ability to repair that life support system. So our astronauts are not only have to be good pilots, they're going to have to know how to repair toilets, HVAC, plumbing, and they'll probably also have to be their own doctors when they get sick. So that's just getting there. In addition, once we get to Mars, we then have to land on Mars. And so you see the 7 minutes of terror that we have for the current science missions that have landed on Mars. That's for something that's on the order of a half a ton, 1 ton at most. We're going to have to put about 30 tons landing our lander on Mars. And right now, we're not sure how to do that other than a standard retropropulsion system, which is very expensive and risky in that environment. So there's no elegant way, really, that we've identified to land on Mars from the trajectory that we have for the Trans-Mars mission. Once we get on Mars, it's a tough place to live. We're going to have to take our own power. It's expected that we'll have a little small fission power system, like a little small reactor that will give us our power, because solar power won't generate it. Your dust storms on Mars, they occur anywhere from an hour to a week, and it can be as long as 4 months. That makes the solar panels pretty ineffective. So we'll have to have a good power system. We'll have to have a habitat that we can repair. Then also we'll be generating our own oxygen from the CO2. We're actually flying an experiment fairly soon where we're going to put a small oxygen generation system on a Mars lander. We're going to generate oxygen from the CO2 through a reduction process. That will be the basis of how we generate oxygen on Mars for both propulsion systems for the return launch or for the crew as they're on Mars. So living there will be a challenge, just getting power, oxygen, water, food to those folks. And then getting home, it's the exact mirror challenge of getting there. You got to get off Mars and get in. That's non-trivial because its Earth is significant. It's not like the moon. You got about 5/8 of that of the Earth. So we'll have a Mars ascent vehicle. You then have to rendezvous with your Mars transportation system. So we get into the Mars transit vehicle, come back to Earth. We have to rendezvous with Orion, and then Orion is then designed to bring the 4 crew back from to Earth. So that in itself is a fairly complex system. Again, over 3 years, the crew is always at risk with respect to medical issues, radiation issues, and failure of our life support systems. So those challenges can be significant, and there's a lot of work to go, as you see, a lot of work to go forward to address those issues. So at the bottom, you're kind of missing the "we need you." The bottom line is I and Tom Zolentz in the second row there won't be here to go to Mars. It's your generation that's going to have to own that, execute, and implement that. So we have a good start here with SLS and Orion. That will get humans to deep space, which hasn't happened since Apollo. But once we get to deep space, there's a lot of work to be done on the habitation modules, on the landers, how to get the environmental life control systems reliable. There's work for another generation, and we expect it's going to take about 15 to 20 years of extended effort. You think that's impossible? Does it sound too soon? Is it too long? In context, Apollo took about 15 to 20 years, right? When President Kennedy said in 1961, I want to see someone on the moon by the end of the decade, NASA already had a head start, okay? We're not going to rewrite the history books, but we were working on that in the early 50s. We started on the rockets, we started on those systems, the designs, how to do it. We've been working on that since the 1950s with the von Braun German team that came over. So Apollo just didn't pop up in 7 years. It was worked on for a couple of decades. Similarly with the Mars, we've been working on it for a while. We'll have a good start with SLS and Orion. but there's still a lot of work left to execute, but with this extended effort, your generation could see you or your children on Mars in some form or fashion. With respect to involvement of A&M, so I don't know if you know, but we got about 70 graduates from A&M working at Marshall. We have a number of contracts, both through cooperative agreements with Dr. Glenn. We have some Space Act agreements where some of the students are working with our patent folks, and we have some activities where we're looking at bearing testing here at A&M through the Jacobs contract. We have a fair amount of work with the folks, and we'd like to grow those relationships more in the future. So the journey to Mars is beginning. Okay, we're getting a good start now. The Obama administration has actually done a good job, and the Congress has done a good job of giving us a stable environment to get to where we are. The expectations are that we'll see SLS and Orion fly, to be successful for deep space missions. It's your generation that will then execute and help us to where we need to go for whether it's Mars or the moon. So with that, I'll be glad to take any questions, comments.
Electrical engineering major here at the university. I was curious, how much training time would it take for the astronauts? You said that they may have to perform anything medically or HVAC or anything dealing with the rocket.
What we're going to do is we're going to send them out with medical directions, medical supplies, and it's going to be obviously somewhat limited. But also we're planning to make some of the medical capabilities in place with 3D manufacturing. So the expectation is on this Mars transit vehicle, you'll have a fab lab, so that if something breaks on my ECLIS system or whatever, I got my CAD drawings loaded in a computer. I then download those drawings. I can make a part on the fab lab, and then I can have an astronaut who knows enough what a wrench is and how to go replace that unit. So there's multiple challenges there. You got to make very complex engineering things simple enough so they can repair them in space. And then you got to have people smart enough on how to do it. So that's a real paradigm change for astronauts. So how long is the training? It's probably forever. You just got to get really smart people who know what they're doing. But it is a mental change in how an astronaut thinks, right? And actually, it's much more the way that the Russians did their astronauts. Their astronauts are not trained as much in contingency operations as they are, and they don't have as many contingency operations on the ground. They kind of make it up sometimes as they go along. I think in this generation, those astronauts are going to have to make up a lot as they go along. We'll prepare them as best we can with, spares, replacement parts, directions, but there's going to be wing it on your own some on your own. Does that answer your question?
Connie, you might be interested to know, and we talked a little bit about this in the office, but that particular project you're talking about, or that series of projects about additive manufacturing and developing parts and things in space, we're working on some of that here at A&M. So hopefully some of that would find its way in this system in the years to come. Also, let me take a minute. I wanted to welcome the additional guests we have here, some from NASA. If y'all wouldn't mind standing up, all the guests we have here from NASA, just be recognized. Go ahead. Our goal is really to, establish a stronger and stronger relationship. It's things like this, it's projects that we work on, it's influence into the classrooms, if you come in and talk to the classes about some of this stuff and really get, the students excited about the future, because we need them to be engaged in it. So we are really happy that we can do this, and we look to keep on doing it. Any more questions before we show our appreciation? So we have a small token of our appreciation that we would like to share with you, and basically says, presented to Dr. Paul K. McConaughey, Dean Speaker Series, November 17th, 2016. So.
Thank you, sir.